what is a retract and what is a deformation retract, and what's the difference between a retract and a deformation retract. So a retract of a space is a subspace such that there is a continuous map from the bigger space to the smaller space that preserves all the points of the smaller space. So this is a quite general definition, and it implies immediately that there is a subjectivity between the pi 1 of the big space to the pi 1 of the small space. As an example of a retract, it can be R2 minus 0 retracts everything on S1. As you see, it preserves the elements of S1. If you pick an element from S1, then this will be still on S1 with identity. Another retract will be the trivial one, a retract to a point. So pi 1 of S1 will give you a surjectivity in pi 1 of 1, which is a 0, and this on 1 it gives you identity. So will be a this is a trivial example of a retract. A deformation retract is a particular example of a retract, and it has much more properties. So a subspace, it's a deformation retract of a big space if the big space can be shrunk continuously to the small space without modifying the small space. So you have a continuous map from x cross I to x such that the identity of x goes to a function in A. So x1, age of x1, it's an element in the small space A, and this particular condition tells you that the homotopy preserves at any time t the space A. So the first remark is the following: a deformation retract is a retract. And how is a retract? You can form a continuous map by taking r of x equals age of x1. This will give you a continuous map from x to A that preserves all the elements of A. So the deformation retracts form a subspace in the space of retracts, a subspace that has much more properties. So for example, the next property of a deformation retract is that it gives you a homotopy equivalence. So for example, R defined on X with values in I and the inclusion of A in X give you a homotopy equivalence between X and A. So J composed with R by the homotopy H, it's a homotopy with identity, and R composed with J is just the identity. So this means the deformation retracts form particular cases of homotopy equivalences. So these are retracts with properties. And homotopy equivalence means actually that pi 1 of X is the same as pi 1 of A. So as you see, the difference between the deformation retract and retract is that the map on the pi 1 is bijective as opposed to only surjective for the retract. So as an example, for example, you can have the point and all the R2. So R2 is contractible, and you can contract R2 to the point without modifying the point 0 by the radial contraction. Another example can be R3 minus z-axis. So for example, you have R3 and you take out the z-axis. Now, if you contract all the lines in R3 to the plane R2, we will obtain R2 minus 0 because 0 is the corresponding of the z-axis, and z-axis is missing from R3, so we don't have a line that contracts to 0. So this means that R3 minus z-axis can be given as R2 minus 0, and this is a deformation retract. All the contraction of these perpendicular lines on R2 minus 0 are preserving the space R2 minus 0. The space R2 minus 0 is not changed. So you have a deformation of the big space into the small space without changing the small space. And R2 minus 0, it actually can be deformed to S1. So you have S1, R2 minus 0 can be deformed to S1 by contracting all the points inside and outside the circle to the circle. And this gives you a new example of a deformation retract.